Hi everyone, my name is Sung-Min Hong and I'm currently with the Gwangju Institute of Science and Technology. It is my pleasure to have a presentation in the first Asia South Pacific MOS-AK workshop. Especially, I want to thank Dr. Grabitsky. The title of my talk today is TCAD-inspired compact modeling approach. The co-author, Mr. Kwang Lee, is a master student in my group. In this presentation, I wanted to discuss about our approach to derive compact models systematically. This is the outline. In the introduction, the motivation of this work is presented. In the second part, our methodology is applied to an arbitrary cross-section of a multi-gate MOSFET. Next, the density gradient model is included in the compact model. After that, the conclusion is made. Introduction. As we know, the TCAD simulation and the compact model share the governing equations. Those governing equations include the Poisson equation for the electrostatic potential and the continuity equations for the electron and hole densities. In the TCAD simulation, we introduce a mesh to describe the semiconductor device, and the discretized differential equations are solved at those mesh points. On the other hand, in the compact model, we build analytic or semi-analytic equations to describe the terminal characteristics. It is my ultimate goal to provide a seamless transition from the TCAD simulation to compact models, at least in some sense. In the industry, there are many application engineers to calibrate their TCAD model devices to the fabricated ones. The calibration is very time consuming, and finally we have a well-calibrated TCAD model. However, the compact models are not much compatible with the TCAD simulation, and we need an additional step called as the parameter extraction to build a well-calibrated compact model. When we have a compact model similar with the TCAD, this step can be simplified. Then, which are the major obstacles to achieve this goal? In my opinion, the most important one is the complicated geometry. In the planar MOSFET, we can consider the vertical direction as the only independent variable. The problem becomes one-dimensional and analytic approaches can be made. However, when the multi-gate MOSFETs are concerned, it is very difficult to set a simple coordinate system. Another obstacle is an advanced physical model. In addition to the basic drift diffusion model, additional physical models are included in the TCAD simulation. Due to the limited model complexity, those advanced models are difficult to be included. Well, the parameter modeling is unavoidable in the compact modeling. However, we can postpone the application of such a modeling until the last stage of the model derivation. By taking this approach, we can keep the generality of derived models. We have recently published a few papers. In this presentation, I wanted to briefly review those works. First, an arbitrary cross-section is considered. Previously, there were several compact models for various cross-sections of multi-gate MOSFETs. Now, we are expecting an error of nanosheet MOSFETs. Its cross-section is complicated. Moreover, the stacked nanosheets have different sizes. How can you model a complicated cross-section. One simple and appealing way is the linear combination. In this model, a cross-section is decomposed into several simpler shapes such as a circle and a rectangle. However, in this approach, the substrate sharing cannot be considered properly. Another approach is so-called a universal model. There are some different names, but the basic idea is the same. For given cross-section, its area and perimeter are extracted. Then, by using these two parameters, we can make a compact model. It has been repeatedly shown that the model works quite well. One example is the BSIM CMG, which is widely adopted. Such a success of the universal model cannot be an accident. There must exist an underlying principle. For that purpose, we define a peripheral coordinate P, and a test function psi is also introduced. The test function is a solution of the Laplace equation with given boundary values. The test function for certain boundary point represents the coupling between the boundary point and a substrate point. By using several test functions, the substrate can be decomposed rigorously. It is noted that those decomposed pieces are overlapping. Therefore, different pieces are connected. We integrate the Poisson equation over the solution domain. The test function is used as a weighting factor. After manipulation, we can derive the Poisson equation written for a piece. It is stressed that no approximation is made up to now. It has three terms: the electric field from the gate contact, the electric field from neighboring pieces, finally, electric charge in the piece. And the first two terms related with the electric fields can be expressed only with the surface potentials. Therefore, even for multi-gate MOSFETs with complicated cross-sections, the surface potential plays a critical role in the charge modeling. The charge in the piece is also modeled as a function of the surface potential. We have applied the proposed partitioning scheme to a rectangular nanowire with a high doping density. In this case, the corner effect becomes significant. For each piece, we can calculate the equivalent oxide thickness and the equivalent substrate thickness. Moreover, the coupling capacitances between pieces can be readily calculated. By using the substrate partitioning scheme, the corner effect can be accurately captured. Of course, in order to obtain this result, we must introduce several pieces. It is not very suitable to the compact modeling. However, it can be shown that the summation over all the pieces yields the equivalent double-gate MOSFET. The next example is the density gradient model. When the electric motion is restricted by a strong electric field or a material composition, the quantum confinement effect becomes significant. Especially in the nanosheet MOSFETs, the electrons and holes move all along the channel direction only, and we must consider the quantum confinement effect. In the compact models, the effect is incorporated in various ways. In terms of physical accuracy, the solvent calculation is desirable. However, the subband calculation is not the standard way used in the TCAD simulation. Instead of that, currently, the density gradient model is widely used. In this model, an equation similar with the Schrödinger equation is solved to calculate the electron density. The figure below compares the electron density calculated with and without the density gradient model. You can clearly see that the electron density is affected by the model. This slide summarizes the model derivation procedure. We have two governing equations, the Poisson equation and the density gradient equation. They are integrated over the solution domain with a weighting factor. During the model derivation, no additional approximation is introduced. As a result, we have some unknown quantities, for example, phi sub omega in this slide. These unknown quantities are modeled following the TCAD simulation result. One interesting observation can be made. When we follow the same derivation procedure for cylindrical GAA and double gate, we have two different but similar equations. The unknown parameters such as the quantum potential at the surface should be modeled properly. For our purpose, it is better to model those parameters as functions of the electron density. The figure shows the quantum potential can be well described as a simple function of the electron density. Cylindrical GAA devices are considered. It is noted that the fitting parameters are dependent on the radius. With the well-calibrated parameters, the integrated electron density can be accurately calculated. Since the charge model itself is exact, a proper parameter modeling can yield excellent agreement with the TCAD simulation. More results about the capacitance and the terminal current will be reported elsewhere. Let me conclude my talk. In this presentation, our recent research effort related with the compact models have been presented. In this approach, we start from the same governing equations. By integrating the equations with the weighting factor, we derive certain exact relation. Then the unknown parameters are modeled. Two examples, the substrate partitioning scheme for an arbitrary cross-section and the density gradient model, have been presented. The key is how to model the unknown parameters. It requires insight, and this is the point where an experienced researcher plays an important role. Thank you for your attention.